I'm Greg from Google, and I'm here to talk to you a little bit about artificial intelligence and machine learning as we're doing it at Google, trying to make it generally useful. I really recommend the CDI report that I think a bunch of you got a copy of. I really enjoyed reading it. I think it's a great starting point. And if you guys also haven't looked yet at the recent White House OSTP report on this, I think that that's also worth looking at. So let me tell you a little bit about machine learning at Google and how it works. So I think one of the things that I really want to underscore for you guys is that this is not the technology of the future, this is the technology of today. This is already in real products and services that users use every day. And this is both taking existing familiar products and services like Google Search and making them better by using artificial intelligence, and also by making entirely new products and services. Like, for example, we launched an automated email responder that's powered by machine learning and artificial intelligence. So what are these fields? How do we think about them? So from an academic point of view, there's a pretty good distinction, which is artificial intelligence is the art and science of trying to make machines that are intelligent, whereas machine learning is a newer, smaller field that focuses on trying to make machines that learn from data or from experience. And while traditional AI systems were programmed with a recipe to mimic intelligence, these modern ML-based AI systems, they're actually given instructions on how to learn rather than how to gain intelligence. And this machine learning approach seems to work much better. And there are familiar examples of all of these things. So IBM Deep Blue, which famously beat Garry Kasparov at chess, was a classic AI system that had almost no learning in it, whereas AlphaGo, the more recent Google DeepMind system that beat the world champions at the more subtle game of Go, was almost entirely learned. It's also worth understanding the distinction between these two fields and a third field, which is the field of robotics. I think there's a lot of hope and optimism that machine learning and artificial intelligence will improve the field of robotics, but we must always understand that these are separate things, and although in popular culture they're often conflated. Just to give you a really specific, concrete example of this difference between artificial and machine intelligence, the way that Google spam detection used to work, which we all rely on to be able to use our inboxes, used to rely on a large set of rules and contingencies about identifying what spam was, and that worked pretty well. But the new system is still a piece of software, but it's software that works in a very different way. It's software that works in a very different way, where now what it does is it has to learn from historical emails to attempt to try to classify them and then change itself in order to reduce errors. And it's really this changing itself to reduce errors that is the magic sounding part of machine learning, but it's actually pretty simple. So let me explain how this actually works. So there's a piece of software that's really just a complicated piece of it's an implementation of a mathematical formula, really, but it's a complicated mathematical formula. It tries to go from emails to predicting whether it's spam or not. And there's a small piece of this software that's actually usually just a table of numbers, which is the modifiable part. That's called parameters. Most of the code is not modifiable. It's just this table of numbers. And there's a separate algorithm that knows how to compare what the machine predicted to what a correct answer is, and knows how to change these parameters so that they're slightly better. And this process repeats many, many times until the systems are kind of good at their jobs. And this block diagram is actually very stable in machine learning. It's been going on for a while, and this is basically how many of the systems are built today, even things that recognize objects and images, which obviously is very different from identifying spam. This has been surprisingly general. This is how computers now understand images, how they recognize speech, how they do machine translation, and how they do all manner of fancy things. In our view at Google, we've seen that in order for machine learning projects to be successful, it seems like we require 4 ingredients. We need computational resources, we need good algorithms, we need training data, we need examples to learn from, and we need creativity and ingenuity. And I'm going to kind of explain the role of these 4 pillars as we've experienced them at Google. So first, training examples. So if you're going to build a spam classifier, you need a historical record of some emails that were and weren't spam for the machine to learn from. And that's really what goes on in this example. And it's effective, but it's very, very gradual. And this kind of learning from examples, is by far and away the dominant style in machine learning today. Technically, it's called supervised learning. There are other formulations like unsupervised learning and reinforcement learning, which may be more important in the future, but they all require some kind of data for the system to work with. So the data piece is important, having training examples, something to learn from. Another thing that's really important here is computational resources. And this is actually the answer to the question, why is this all happening now? Why is AI suddenly successful in the last 5 or 10 years and has been silent or been in a winter for a while? And this actually sort of reminds us of the, oh, my clicker's dropped again. I think something's going to sleep or something. I hope you all aren't going to sleep yet. Okay, anyway, this reminds us of the quest for human flight. So we didn't know this at the time, but in the 1890s, it wasn't possible to fly. There were a lot of people out there trying, and they were doomed. They didn't know that they were doomed. Turns out that the reason that they were doomed was because the power to mass ratio of the internal combustion engine was insufficient. Engines were too heavy and too weak. So if you're trying to build a flying machine, it just wasn't going to work. 10 years later, it was just possible. And 15 years later, it actually started being kind of easy. And indeed, the first people to fly were people who built their own engines to be as light and as powerful as possible. Nobody knew that that was the missing link, but that's what it was. Well, the same thing happened with machine learning. Many of the algorithms that we use have been sitting around in the literature, and they've just been waiting for CPUs to get fast enough through Moore's law, or for people to realize that they could get access to cheap computation in the form of graphics cards, or at Google, we're also building our own silicon chips it's kind of like building your own engine to just kind of maximize performance. These things, the availability of cheap computation, is really why this is happening today. The next thing that I want to talk to you guys about is tools and algorithms. So most of the real algorithms here have been around since I was a kid. Like these are not, it's not that there have been gigantic new mathematical breakthroughs. They've been around for a while, but good implementations of them haven't been. And so one of the things that we've done at Google is we've collected a lot of the basic tools and algorithms that are necessary in a package called Tensorflow. It's a software package that we use internally, and we also give away as an open source tool. We only released it in just a year ago, and it's already the #1 repository on GitHub, the open source sharing site for machine learning. And the reason for this is that this is actually a second generation approach. This is not the first machine learning toolkit that anybody's ever built. And in fact, it's not even the first one that Google has built. But this second generation of things, we've kind of got it right, and it's nicely reusable. It's one system that's flexible enough both for researchers and graduate students to use, and it's also robust enough to use in real products. And this is what Google uses in our products, but we're releasing it externally with the Apache 2 license, which, if you're not familiar with it, is very liberal. It allows you to use it in industry and education, in your own startup, or as hobbies, whatever you want. But at TensorFlow, we're also trying to educate the engineering community about using these new techniques. And so there's this thing called playground.tensorflow.org that you can go to, and you can teach yourself about technologies like artificial neural networks without writing any code. It just runs in the browser, and you click the little play button, and the machine learns. It's kind of fun. So, okay, that's a little bit about tools and algorithms. But then the most important ingredient, and the thing that I think is really the rate limiting step right now in how this technology is being adopted, is ingenuity and creativity. It's critical to understand that AI is not something that you can buy in a box. And if someone's trying to sell you AI in a box, you should be very suspicious. Because what this really is that it's a new set of tools, and it's about how we use these tools to build new things in the world. And so at Google, we've seen this kind of explosive growth within Google of people using machine learning to make their own products and services better. And this is not by applying some monolithic approach, it's just by giving them the computational resources, giving them tools that they can use, and then them having their own ingenious ideas about how it can be used to improve their products and services. And in fact, one of the main machine learning technologies that people are excited about right now, which is this stuff called deep learning. Deep learning is almost a Lego set for building machine learning systems, where these are composable building blocks that allow you to make new kinds of predictions, and you can put them together to build interesting things. And indeed, the system that actually recognizes objects in images at Google isn't, the one yellow box that I showed you before that just cutely said, machine, the model, or whatever. It's actually this very complicated set of individual pieces that all work together. And if you go to machine learning conferences, you largely see people coming up with new ways of combining the Legos and comparing them. It's actually relatively rare that people even suggest a new Lego. But this stuff really works and works in real products. So in Google Photos, you can search for anything in your photographs. You can search for hugs or puppies or whatever, and find all your examples of those things. And this would have been science fiction just a few years ago. It's also doing surprising things like giving artists new ways of creating creative images. It's doing things like winning at the game of Go. And it's also doing some things that are surprising, like this automated email responder, which we were really surprised that, so in 2009, some people at Google made a joke that, a prank, April Fool's Day joke, that Gmail is going to start responding to your emails for you, because it was absurd in 2009, genuinely absurd. And 6 years later, we launched it to everybody, and 6 months after that, it was 10% of all replies on mobile inbox. And this technology, which one of the things that's exciting about this is that we publish how this works, and we explain how it takes emails and gets responses. But one of the things that's interesting to understand is how these technologies are sort of able to move quickly, is that we can take very similar ideas and apply it to a problem like machine translation. It's a very similar mathematical model, and indeed we just announced last month that we're getting big improvements on our quality of being able to make translations better by using this technology. And just to underscore even more how the building blocks work together, it took a very small number of engineers to be able to combine Google's computer vision system with its machine translation system to make these kind of like otherworldly augmented reality tools that automatically translate text in other languages. And another example is like you can now do this thing with the Google Now app where you can point your camera at something and then ask Google about it, and that's using speech recognition and image recognition and Google search and all kinds of, a whole set of components and products, all of which use machine learning and artificial intelligence in some way. So machines are already making a positive difference in a lot of products and services, but I really feel like this is just the beginning. Like we're just kind of figuring out what these new tools are and having a few ideas about how we can use them. But we think that we need to get as many people as possible able to use these new tools so that they can apply their own ideas. So one way that we're doing this is we're trying to make our tools available so that others can use them. We release our software. We give our software away for free, and we rent our hardware through the cloud machine learning products at Google. So through cloud machine learning, a programmer who isn't that familiar with machine learning can reuse our components, like our computer vision system, just by making a call to a Google Cloud server, or they can actually work more like a Google engineer where they can use TensorFlow and run it directly on cloud. They can also run TensorFlow on Amazon or Azure or anybody else's cloud. But I want to give you one crazy example that I heard recently to underscore this creativity point about a brilliant, wonderful nerd in Japan who decided to help his parents' cucumber farm by building an artificial intelligence system to sort cucumbers. Evidently, his mom spent many long hours sorting their cucumbers into different sizes and shapes, and she wasn't really keen on doing that work anymore. So his creative idea was, I'm going to use AI to solve this problem. He happened to use TensorFlow as the software that he used. For computational resources, he used an open source controller called Raspberry Pi, Google Cloud. And for training examples, he just took some pictures of cucumbers from his family's farm and used those as examples on how to sort things. And he built this kind of crazy cool robot that, that sorts cucumbers based on their size and shape. It's not anything that anybody at Google ever would have thought of, but this is basically a hobbyist seeing that there's an opportunity here, and we need to get these tools out there so that people can reuse this. So shared tools is one thing, but I think the other thing that's really important is shared knowledge, teaching people how to use this. So this means publishing. I think that right now there's a great environment where both academics and industry researchers publish their research on how they're making AI work today, but it's also through community education and through funding of research and students. But this publishing stuff is actually really important. And at Google, just in the last 4 years, our little deep learning group has published over 90 papers. And there are many more from the rest of Google research. And there are many, many more from the rest of industry. And many, many, many more from the rest of academia. And this is really critical because we're in this early phase of development. I do want to call out, since I know there are a lot of policy people that are interested, people who are interested in policy here, about some, I think it's really great that the community is starting to focus on some issues that are thorny, but really important to look at a technical level. So for example, we have a couple of papers on AI safety and on AI policy. So one of the papers that we had earlier this year is one that tries to lay out and formalize concrete problems about what are the possible challenges that we might face in the coming decades when it comes to safety around ML and AI systems. These aren't problems that we face today, but we might as well be technical and serious about, well, what problems could arise in a few decades, and start thinking about possible solutions. Another thing is we have an even more recent publication about dealing with fairness in machine learning systems. So a central observation, an important thing to understand, is that even if the code of a machine learning system is completely unbiased, if it learns from data that contain the shadow of unconscious bias from humans, the machine will learn to recapitulate that bias in its own decision making. And this paper gives us mathematical tools to inspect and analyze and test whether a machine learning system is biased, and tools to potentially correct it without ripping it apart. This is just one paper in this area, but this is the kind of thing that we need to think about, is how do we address these concerns? It's not that it's not a problem, it's that it's a problem that we should address. Related to this, a bunch of companies have gotten together and started a new nonprofit that's called the Partnership on AI to benefit people in society. That's kind of a long name. I just say PI for short. And the point of PI is to try to create a space for people to have these discussions about the impact of AI on people and society, and what our best practices and best approach should be. So the final takeaways, the things that I hope that I communicated to you very early in the morning. So the differentiation between AI versus machine learning versus robotics, this is important to understand. Machine learning is definitely not magic. It's just a tool. And when you give craftsmen a new set of tools, they make things that are really beautiful. Machines learn best from examples. This is really one of the things that we've seen over and over again. It's not like they just chew on some amorphous body of data and gain insight. You actually have to show them, I want you to do this, and then give them millions of examples of that, and then they learn to do that one thing. Why is this happening now? It's because computation is finally cheap and fast enough. Making machine learning work in practice seems to require these 4 things: creativity and ingenuity, computational resources, examples to learn from, tools and algorithms. But the current bottleneck is in the creativity and ingenuity, getting enough people trained to be able to use these tools. All this other stuff is a commodity now, except for the human capital. Tensorflow is one example of us trying to make the tools available to eliminate that as a bottleneck to progress. And there are challenges here, but I think it's pretty obvious that the challenges are best faced openly and together. And standards like open publication of how machine learning systems really work, and talking frankly about what the real challenges are, but in an intelligent way as opposed to a science fiction way, is really important. Thanks, that's it. And I think we're doing 5 minutes of questions. I talk really fast, so hopefully you can just ask me to repeat something. Yeah, over there.
You mentioned there's Lego blocks. How many Lego blocks are there? I'm sorry.
Oh, how many Lego blocks are there? So that's a great question. So it's very hard to define exactly what, so the Lego blocks that I refer to are actually components of mathematical functions that can be fit together to build more complicated functions. And I would say, depending on how you count, they're either tens or maybe a couple of hundred of these individual components. The funny thing is that the constraint on these components is a funny mathematical property called differentiability. Currently, the way that these systems work is that you can build any complicated formula you want, and as long as you can compute its derivative, which if you remember from calculus class, you don't have to, I promise. As long as all of the components have derivatives, then you can combine them all together and you still have a derivative. And you can make really complicated things as long as you work within this constraint. So people are thinking of new ones, but there really aren't a terribly huge number. Yeah, here?
Yes, question. I'm pretty good with the alphabet, so what is TPU?
Oh, yes, TPU, sorry. So TPU is Tensor Processing Unit, and it's just Google's custom hardware for doing machine learning.
Is it RISC-based?
Hmm?
Is it RISC-based?
It's a custom ASIC, and I think that's all I say about it. I'm not a hardware guy, like it's just totally magic to me. I'm like, great, it's fast.
So there's a bit of a rhetoric that's emerged around deep learning and an inability to explain the models that are learned through that process. I wonder, do you think that's a real challenge? Is it a challenge that Google is interested in solving? Is it solvable at all? Can we make headway on that?
Oh yeah, so this is a great question. So I'm glad you asked. So it is worth understanding that different machine learning algorithms have different levels of explainability. Some of them are easier to interpret, some of them are harder to interpret. You can do things that are very, very interpretable and slightly less powerful, like decision trees, or you can do things that maximize power and give up some explainability, like deep learning. So it is true that deep learning is less explainable than some of the other machine learning options that are available today. But it's also true that progress in making deep learning systems explainable and understandable is very, very rapid. No one was working on studying explaining how they worked because they didn't work. Now that they've started working, people are like, oh wow, let's figure out how this thing works. And I'm actually really excited and impressed with how quickly we're making strides in that. Some of those researchers are at Google, but a huge fraction of them are not. And that's great because you go to conferences and people have figured out new ways of taking an existing deep learning system and explaining it, or even better, building a new variant of the deep learning system that is intrinsically more explainable. So it's a challenge to face, but the nerds are running it down. It's great. Yeah, over there.
What kind of educational backgrounds are best for people working in machine learning?
Okay, so what educational backgrounds are best for people working in machine learning? So the good thing is that this has not been a field of study for any amount of time. So presently, it's basically anything. It needs to be. It requires the same skills that we see in job titles like data scientist, right? So you need to be able to program to some degree because these things are all still expressed in code. But most importantly, you actually need to be able to think critically about data and be creative to find solutions for how to put things together and know a little bit about statistics, a little bit about computer programming, but mostly thinking about data and solving problems. But on my team, we have people with math backgrounds, physics backgrounds, neuroscience backgrounds, no formal education whatsoever. I really think that it can be almost anybody. Yeah?
As a follow-up to that, there's this tension between the academic and industry communities about competition for talent. That academia thinks that we're losing machine learning people to companies.
Yeah.
And how does Google do that economy, or how do you address that?
Yeah, so I actually think that the central problem is that there's insufficient supply of people knowing how to do machine learning. And I think it's the same thing that happened, you know, when people realized, oh, this internet thing is going to be cool. And then they realized that there weren't actually that many people who knew how to build web pages, right? And, you know, there was a shortage of supply of people who knew how to do this. And I think that the same thing that happened in computer networking and computer security, that's happening right now in machine learning, but the response to this should clearly be to educate people everywhere. I don't think only in academia and universities, but whoever is excited and passionate about this. Are we out of time? We're out of time. Okay. See you. Thanks.